In this Federated Marine Spatial Data Infrastructure pilot project, the University of Calgary team demonstrates interactivity between a discrete global grid systems server and an end-user client application using Open Geospatial Consortium Discrete Global Grid System standards. A discrete global grid system is an Earth reference that uses a hierarchical tessellation of equal area cells to encode geographic information, providing integrated geographical data on demand. The OGC DGGS server cluster used in the pilot project operates 6 modules to facilitate data discovery, encoding, storage, processing, visualization, and sharing. DGGS are data agnostic. They are designed to integrate data values across all spatial resolutions, reference systems, formats, and data types, rendering them analysis-ready. A cruise ship enters the Bering Strait. Passengers wonder what the coast will look like as the sea level rises and the permafrost that supports the coast recedes. While the passengers ponder the future, the crew plan their route. The DGGS ingests over 150 gigabytes of marine and terrestrial geographic data to answer their questions. S102, GEBCO bathymetry. S121, maritime limits and global administrative boundaries. Center for International Earth Science Information Network's grid population of the world. S122, World Database of Protected Marine and Terrestrial Areas. Global Land Institute's global land cover. S412, Weather and Sea Ice Conditions. Mean Annual Temperature and CMIP6 Change Model. National Snow and Ice Data Center's Map of Permafrost. USGS's Geologic Map of Alaska. And S124 NOAA and U.S. Coast Guard's AIS traffic and navigational warnings. These data values are sampled and quantized into the DGGS cells, ready for 3 primary OGC API operations: calculate, explore, and search. Passengers calculate temperature change by subtracting the current average annual temperature from a model of future temperatures. Composing mathematical expressions is like entering a formula into a spreadsheet. A new data source is created. Passengers explore. Their selection generates the Yukon River watershed. Data values are aggregated and returned as spatial statistics and feature lists. Climate, permafrost, land cover, protected areas, populations, geology, wildlife, topography, and even real-time sensory and predicted data like rainfall intensity can be accessed to characterize the watershed with the OGC Environmental Data Retrieval API. What is here? Select Alaska. Where is it? Where are the protected areas? The passengers search complex relationships to find unknown places. They can use the OGC DGGS API to explore and then exploit these data connections by drilling down and filtering through them. They notice a significant temperature rise is predicted. They can explore other connections. Where are the protected wetlands? Particularly those along the coast. Where will the worst changes occur? The questions, what is here? And, where is it? Are fundamental duals that connect curious humans to their environment. The passengers turn their attention to the coast as they cruise into Kotzebue Sound. What will this low-lying area look like when sea rises? Where will the sea inundate the coast? How many people live here? Where are the changes expected to be the most costly? The crew will be asking similar questions. Shipwrecks are not uncommon. With S100 universal hydrographic data sources containing historical, derived, and real-time information, a model of the risk will help assess navigational routes. Shallow sea depth, marine protected areas, high-density vessel traffic, marine life, and other cautions provided by NOAA and the U.S. Coast Guard are mashed up and parameterized to prioritize risk. OGC Open APIs and the DGGS standard provide a simple mechanism for building applications that require multiple sources of geographical data on demand. Thank you for your interest in the Federated Marine Spatial Data Infrastructure pilot project.